Hey everyone, in this video we're going to learn about step functions. Now a step function is a special case of a piecewise defined function. So our first example, graph the following piecewise defined function where f of x is defined as -3 on the domain -5 is less than or equal to x, which is less than -1, 2 on the domain -1 is less than or equal to x, which is less than 3, and 6 on the domain 3 is less than or equal to x, which is less than or equal to 8. Okay, so practice graphing a piecewise defined function. Our first piece, we're going to graph y equals -3 on the restricted domain, -5 is less than or equal to x, which is less than -1. Okay, so we'll get 2 points on this line. So the first point is -5, -3, right? When x equals -5, y is -3. Second point is -1, -3, coming from the other side of our restricted domain. We'll plot those 2 points. So -5, -3, closed point. -1, -3 is going to be an open point because x is not equal to -1. And we connect those 2 points with a horizontal line. There's our first piece. Next piece, y equals 2 on the restricted domain -1 is less than or equal to x, which is less than 3. So since we have a bounded restricted domain, just like we had in that first example, let's just find 2 points. So when x is -1, y is 2. When x is 3, y is also 2. At -1, 2, we have a closed point. It is equal to -1. 3, 2, we have an open point. And we connect them with a horizontal line. And then we have y equals 6. On the restricted domain, 3 is less than or equal to x, which is less than or equal to 8. So the 2 points there would be 3, 6 and 8, 6. So at 3, 6, we have a closed point. At 8, 6, same thing. Connect them with a horizontal line. And there we have our first step function. So a step function is a piecewise defined function where all the pieces are constants, or, looking graphically, horizontal lines, or pieces of horizontal lines. So, formally defining a step function, it is a piecewise function in which each function is a constant function. And the reason it's called a step function, if we look at that last example, they look like steps. So write a piecewise defined function to represent the following step function. They've given us a graph. Okay, so we'll define f of x. We need to define 3 pieces for each part of the step function. So the first piece, well, that's part of the graph of y equals 4. So the first piece is 4. On the domain, -6 is less than or equal to x, which is less than or equal to -2. The next piece is y equals -1. So -1 is our next piece. And that's on the domain -2 is less than x, which is less than 2. And the last piece is part of the graph y equals 1. So we put 1 into our piecewise function. And that's on the domain x is greater than or equal to 2. It extends infinitely along the x-axis. Okay, so there we have the equation of our step function. Now in this case, notice the steps kind of jump, right? It goes from 4 to -1 back to 1, but it's still considered a step function, even though in this case it doesn't look like a set of stairs, right? We use the word step function to describe any piecewise function that's made up of only constant functions. So how could this be useful to us? Let's look at a word problem. Carrie wants to go kayaking. The table below shows the prices a rental stand charges for use of its kayaks for any length of time up to and including the time listed in minutes. So we see the minutes from 0 to 15, including both 0 and 15, they charge $10. From 15 to 30, including 30, they charge $20. 30 to 45, including 45, they charge $25. And from 45 to 60, including 60, they charge $30. Okay, so there is their table for how long we're renting it and how much they're charging. And the question asks us in letter A to graph the step function that represents the price of using a kayak for up to and including 60 minutes. Okay, so we have our minutes axes that's going to be t. And our cost axis, we'll let that be y. And that's in dollars. Okay, so our minutes axis, we need to go all the way up to 60. So if we go by fives, we'd only get up to 50 because there's 10 boxes here. And if we look at how the minutes are broken down, they're in chunks of 15. So that this is nice, let's go every 2 boxes is 15. Then we have 30, 45, and 60. So that will allow us to graph each piece nicely. And we need to get up to 30. So if we go by fives, that will be sufficient. So we'll go by 5. So then we have 10, 15, 20, 25, 30, 35, 40, 45, and 50. Okay, so the first piece, the first step of the function, we're graphing from 0 to 15, including both. So we'll have closed endpoints, and the cost is $10, right? So it's like we're applying the point 0, 10, and 15, 10. So 0, 10, 15, 10, and we're going to connect them with a horizontal line. Right? We're charged the same amount for any time within 0 to 15. And then, graphing the next piece, we'd be applying the point 15, 20. So that's going to be an open point. And then 30, 20 is a closed point, and we connect them. Next piece, 30, 25 with an open point, and 45, 25 with a closed point. Connect those pieces. And then we have 45, 30 with an open point, 60, 30 with a closed point, and we connect them. I didn't list all the points out, but hopefully you can follow that logic. Okay, we're connecting with horizontal lines because the price doesn't change within that time interval. And if we notice, the fact that this is a closed point and this is an open point means if we use it exactly 15 minutes, they're going to charge us the lower price. Once we go past 15 minutes, so let's say 15 and a half minutes, then we're going to jump up to the next price, which in this case is $20. And the same behavior would happen when we're transitioning to 30 and past 30, and 245 and past 45. So here is our step function that represents the cost of renting a kayak for up to and including 60 minutes. So if someone used a kayak for 35 minutes, what would be the price? Well, 35 doesn't fall nicely on our axes, but it's somewhere between 30 and 45. And if we go up to our graph, any point between 30 and 45 is going to be $25. Okay, so it will cost $25 to rent a kayak for 35 minutes. We could also answer this question off the table, right? Look for which restricted domain 35 falls into, which is this third restricted domain, and then look at the cost. Okay, so we have a couple of ways we could approach that problem. But this is a perfect example of where a step function is useful, right? It's not linear. They're not charging us a certain amount per minute. They're saying, okay, if you rent from 0 to 15, it's one flat fee. 15 to 30, including 30, one flat fee. So it works out to be a step function. Now there are two special types of step functions that if you study enough mathematics, you're going to see used. And that's the floor function and the ceiling function. So the floor function, also called the greatest integer function, takes the input and rounds it down to the closest integer. Okay, so for instance, if we put in 2.1 as the input here, we would round down. So let's write that, f of 2.1. Okay, so think of the integer right before 2.1. That's going to be 2. F of 2.1 equals 2. So this is also called the round down function. Even if this was 2.9, right? So if I change this to 2.9, I'm still going to round down to 2. And then the ceiling function rounds the input up. I should change that too. Okay, so if we had f of 2.1 to start again, and now we're taking the ceiling of f of 2.1, okay, so round up. 2.1 is the input, go up to the next integer. That would be 3. And I like the notation here because if you look at this, there's two little parts of the bracket here which are below the variable, kind of like the floor. And in comparison, for the ceiling, there's two little pieces of the bracket above the x, like a ceiling. So visually, we can actually remind ourselves whether we're dealing with the floor or the ceiling function. Okay, so let's practice with these. If f of x equals the floor of x, evaluate the following. Okay, so if our input's 2.8, what integer comes before 2.8? And a good tool for this is to use a number line. Right? Think about 2, 3, 4. If I put 2.8 on the number line, that'd be like right there. Okay, so round down to the integer on the left. So that would be 2. F of 4.1. So 4.1 is like there. What integer comes before 4.1? We round down, and we'd round down to 4. Now this is an interesting one, f of 6, because 6 is an integer. So that's actually a nice input, because the integer below 6 is 6, so it just stays. Not sure what that number was. 6. And then we have f of negative 1.5. So again, I'm going to draw a number line for this one. So we're going to have negative 2 and negative 1. We'll focus just on that spot. So negative 1.5 is right there in the middle. Okay, so remember, round down, we're always moving left on the number line. We're going this direction. So what integer is below negative 1.5? Negative 2. Okay, so f of negative 1.5 is negative 2. So now taking the same inputs, but now evaluating the ceiling function, f of 2.8, so what integer is right above 2.8? That would be 3. F of 4.1, we round up. So round up to the next integer, that's going to be 5. If we input an integer, we just get that same integer out. And f of negative 1.5, again, I'll use the number line here to illustrate what we're thinking about. So we have negative 1.5 right in the middle, so we're rounding up. We're moving to the right on the number line. So we'd round up to negative 1. And again, for any of these examples, feel free to draw the number line. I think it's helpful to visualize what we're trying to do. So let's look at a graph of the floor function to see why it's considered a step function. Okay, so if we think about this, any input from negative 2 up to negative 1, not including negative 1, is going to round down to negative 2. We can see that on our graph. Then if we input negative 1, so remember, f of x is equal to the floor function. Input negative 1, we output negative 1. Input negative 0.5, we'd round down to negative 1. Right, so there are all our outputs. Any input from negative 1 to 0, output's negative 1. Until you get to 0, the output's 0. And that pattern continues. And this is a great illustration of why it's a step function. Now this is just a piece of it, right? It would continue, right? There would be, here I'll draw here, negative 3 goes, right? Continues infinitely in both directions. Okay, this is just a part of the graph. For each of the following situations, write a function using either the floor or ceiling function. First example, at a local hardware store, you can rent a paint sprayer for $15 an hour, charged by the full hour, plus a $40 cleaning fee. Okay, so what this piece means is they're only going to charge us by the full hour. So for 1 hour, for 2 hours, for 3 hours. So if we rent it for 1.5 hours, 1.5 hours, we've passed 1, they're going to charge us for 2. So we're going to need something in our function that rounds our input up to the next full hour. Okay, but let's start by defining our let statement. So let x be the number of hours that we rent the paint sprayer for. So we'll say our function f of x is equal to, okay, so it's $15 an hour charged by the full hour. So if we did 15 times x, well, that would be simple, but then we're saying we could plug in 1.5, but they're not going to charge us for 1.5 hours. They're charging us for 2. So what can we use that would take our input and round it up to the next full hour? Well, that would be the ceiling function. It's a perfect time to use the ceiling function. So we'd have 15 times the ceiling of x plus the $40 cleaning fee. Right, so if we rent the paint sprayer for 3.1 hours, well, they're going to charge us for 4. We pass the 3 mark, they're rounding up. Okay, so if we plug 3.1 into the ceiling function, we'd round up to 4, multiply by 15, and then add on the 40. Okay, so this is a nice example to see a use of the ceiling function where if a store wanted to create a function that all they have to do is input the number of hours you rented it for and they would get out how much they have to charge you, this would be that function. The next example, Miss Newton is ordering birthday cakes for her son's birthday party based on how many people attend. Each birthday cake costs $25 and will feed 12 people. Okay, so we're going to define the variable to be the number of people that are attending the party. Okay, so then how much she's spending on the birthday cakes is f of x. Now she's going to spend 25 each. But how do we figure out how many birthday cakes she's going to order? Well, each cake feeds 12 people, and there are x people coming. Okay, so we want to divide x by 12 to get the number of birthday cakes. But what if it doesn't go in perfectly? Like, what if we had 13 people come to the party? Well, 13 divided by 12 is 1 point something. Right, it's not perfect. So in that case, we'd have to buy 2 full birthday cakes. Right? We can't let that 13th person not have cake. So we'd have to round up. Right? If 26 people came, 26 divided by 12, 12 doesn't go in evenly. Right? It would be 2 point something. Well, we need to buy 3 birthday cakes, so everyone is fed. So we have to round up again. Okay, so what we're going to do to figure out the number of birthday cakes is we're going to take the number of people divided by 12, and what we get from that, we're going to round up. Well, round up means we're going to use the ceiling function. So how much Miss Newton's spending on birthday cakes is going to be 25 times the ceiling of x divided by 12. So again, 24 people come. Divide by 12, that's 2. Ceiling of 2 is 2. Multiply by 25, she has to spend $50. Right, but if 30 people come, 30 divided by 12, well, 12 doesn't go into 30 evenly. It would be 2 point something extra. So we'd have to buy 3 birthday cakes. So we take that value, round up, do the ceiling function, and multiply by 25. All right, so that concludes step functions and our functions unit. Okay, so step functions are a special case of a piecewise defined function. We're really going to focus more on graphing those step functions and running the equations, opposed to the floor and the ceiling function, but I think they're nice extensions to see because they are step functions. So with that, do a few problems, practice, and make sure you're confident with the material. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.